Okay, let's begin. Hello, everyone. Welcome to our session on machine learning for decision making and development evaluations. My colleagues and I are going to talk about using Causal Forests, which is a machine learning methodology for treatment effect heterogeneity analysis. Just to share a little bit about our team. We are from 3IE, the International Initiative for Impact Evaluation. We have Fiona Kastel, who's a senior research associate at 3IE, Geetika Pandya, who's also a senior research associate, and me, Devika, who's a data scientist at 3IE. Just to give a bit of a background about the organization, if you have not heard of us, 3IE promotes evidence-informed, equitable, inclusive, and sustainable development. We support the generation and effective use of high-quality evidence to inform decision-making and improve the lives of people living in poverty in low and middle-income countries. We provide guidance and support to produce, synthesize, and assure the quality of evidence of what works for whom, how, why, and at what cost. And this is especially, the last part is especially relevant to today's presentation because we're interested in understanding impact evaluation at a deeper level and what is working for who, as we'll explain shortly. Now to touch upon a little bit of the machine learning aspect of today's talk. There are various ways to use AI, machine learning, and big data across the program cycle. As you'll see, these are sort of the rough steps of a program cycle. You define the needs and goals of the program or the intervention, identify responses, design and plan the intervention, implement the intervention, and then evaluate what worked and what didn't work and for whom. And as you can see, there's several different ways in which you can integrate or apply machine learning across this cycle. From the latest ChatGPT chatbot to query evidence to web crawling and web scraping to computer vision and using use of satellite imagery to kind of enhance our data evidence base. And the ones that we've highlighted in blue are some of the things we're currently working at. At 3IE, we have a dedicated data innovations group that constantly tests out these new methods. And today we're going to talk about one such method, which is particularly useful at the evaluation stage of the program cycle, as today's talk is mainly about, how can we improve and bring innovations to evaluation. We're going to talk about causal trees and causal forests for treatment effect heterogeneity analysis. So just to give you an overview of what we're going to be talking about today, first we'll get a little bit into what is the importance of treatment effect heterogeneity, who cares about it and why, how can we use a machine learning based approach to heterogeneous treatment effects analysis beyond just what we've been doing traditionally. We'll demonstrate this method using a case study of the breakthrough project in Haryana, India. This was a 3IE funded study, so we will be using that as an illustrative example. And then talk a little bit about applying this to policymaking in the future and how all of you could also potentially implement this in your work. So let's talk about machine learning for impact evaluation. What is the most important thing in an impact evaluation is obviously we want to understand the average treatment effect. What was there a positive impact of the intervention? Was there a negative impact? And that's definitely important, but in recent times, we've also realized that we want to go beyond the average treatment effect. We often want to know how the impact varied for different groups of individuals, who benefits most or least from the intervention. And traditionally, we select some standard criteria to test heterogeneity on, like gender or religion or occupation. We're all familiar with, doing some kind of heterogeneity analysis when we're doing evaluations. But there are various intersecting aspects of a person's identity, background, and environment that can influence how they interact with the intervention and their outcomes. So for example, you see in this word cloud here, all of these different aspects of a person's identity can intersect in linear and nonlinear ways that are sometimes hard to capture with pre-specified sort of standard criteria to test heterogeneity. We might miss something. We might not realize that there was a important subgroup here. So how do we kind of address this? And what we've also learned from our work at 3IE is that decision makers have this need of looking at the intersecting identities of people. They want to go beyond that average treatment effect. And how do we address this? They want to make sure that all the members in their community benefit from the positive impact of an intervention. So not only do we want to make sure that everybody is having a positive impact, but also our goal is to look out for the intersectional identities of individuals that can often push them to the margins and exclude them from the positive impact. So a heterogeneity analysis helps us find out if the intervention actually had an impact on everybody in the community, and if yes, then was it a similar impact? Was there some people who benefited more or less? And kind of collate that with the identities of the people to make sure that we're not pushing people to the margin or losing out people in terms of the benefits they receive. This diagram here is something that we adapted from the Equality Institute's version of the intersectionality wheel and got it from the UN Women's Guidebook. And you can see here all the different ways in which a person's identity, right from infancy to old age, religion, education, disability, geographic location, all of these things intersect. And our goal is to sort of account for all of these different ways of intersecting identities in our analysis. One question we may ask is, can't we achieve this with our traditional heterogeneity analysis that we do? Yes and no. There are certain technical challenges with the traditional heterogeneity analysis when it comes to addressing this particular need of decision makers. First is that it can be data hungry. Subgroup analysis can be clunky and time intensive. So if, for example, you say, okay, let us split it on gender, now let us split it on religion, now let us split it on education, you're like doing a million regressions. It's really time intensive. Sometimes you're trying to do intersectional identity analysis, and so you can imagine how many different regressions you'll have to run. You also run the risk of p-hacking and multiple hypothesis testing because you're trying out different hypotheses, and maybe some of them work, maybe some of them don't work, and you might have a lot of false positives. And if you are feeding a lot of interacted variables in a linear regression, as many of you I'm sure have experienced in your work, is you start losing power because you don't have enough data to get statistically significant estimates on each one of those interactions. The other problem can be that it's very researcher driven, the way we do heterogeneity analysis traditionally. We tend to pre-select a handful of covariates based on a theory, and then just do our subgroup analysis on those covariates. But those covariates might be correlated with some others that we may miss. And although we definitely want to have some theory in mind, we want to base our hypotheses on theory, we may miss out on some interactions, or we may be using something that's just been used for a long time. So this is an opportunity for us to reimagine and rethink how we could do our heterogeneity analysis. That's where machine learning methods come in. They can help mitigate some of these risks. They can help address some of these problems and challenges that we have. The main idea here is that we let the data indicate which combinations of characteristics result in different treatment effects. What this might do is we might find heterogeneity where we may not expect it, especially in complex environments. And some of the methods here are listed here, such as lasso or causal trees and causal forests, especially from the Athey and Wager and Imbin's school of literature. There's a lot of new work that's been done on estimating treatment effects with causal forests. So that is what we're going to focus on today. But all of these methods kind of have this benefit that they allow for treatment effects to be nonlinear and the expected drivers of heterogeneity do not have to be defined completely ex ante. So we kind of let the data drive the analysis. So today I'll get a little bit into what causal forests and causal trees are. We won't be talking about lasso as much, but you could definitely look it up online and potentially use it in your work. So what is a causal tree? And I know some of you might have questions about, technical questions, so please leave them in the Q&A and we can get to them at the end. Just make sure you remember it and log it there. So yeah, what is a causal tree? Basically what this is doing is it's trying to take all the different characteristics of the sample that we have fed the model and split the sample into these groups at the end here in such a way that each group's treatment effect is as distinct from the other groups as possible. So that is sort of the goal of the machine learning algorithm, is divide up our data in such a way that group 1's treatment effect, average treatment effect, is as different from group 2's average treatment effect, is as different from group 3's average treatment effect, and so on. And it does it in a way where it takes every single characteristic that we provide and splits the sample on each one of them, such that we get as much variation in average treatment effect between the different groups. I know this is a little bit difficult to understand if you're not familiar with decision trees in general. So if there's anything you want to take away from this slide, is think of it as you're feeding the machine a lot of different characteristics. It's taking all the characteristics and trying to figure out how do we split the sample in a way that we understand or we get the most heterogeneity. And here you can see it's splitting it on income, age, education, political views, marital status. This is from a tutorial from Stanford. We got this image. And then you might wonder what causal forests are. Causal forests are nothing but an aggregation of trees, as you might think a forest is an aggregation of trees. What it's doing is it's resampling from the data a multiple number of times and generating many, many trees, and then aggregating the information from all of these trees to create what we're going to call, or what Athey and Wagger and Embeds call in their literature as conditional average treatment effects. So what that's going to do is for every single group that's created, every single subgroup that the machine creates, you're going to have an average treatment effect, which is going to be called the conditional average treatment effect, or the CATE. And what that helps us do is it tells you, okay, so for example, if we have a group of people who are, say, under 55 with a high income and certain types of political views, and this is this first group over here, they're going to have minus 0.43 average treatment effect for that group. And so you can see how this is similar to a traditional analysis, except that now the groups are being created by the data itself. And now we want to show you a case study where we applied this causal forest. I'm going to hand it over to my colleague, Fiona.
Great, thank you, Devika. Yes, so let's look at this causal forest method applied to an example. And so we applied this method to a previously completed impact evaluation. Let me just make sure I can. Okay. So this impact evaluation was a gender attitudes change program in Haryana, and it was essentially a 45-minute school-based, discussion-based session within a school that attempted to change gender attitudes or improve gender attitudes, as well as girls' educational and career aspirations and self-reported gender-related behaviors. And this intervention was implemented in 314 schools, or randomized within 314 schools with about 14,000 secondary school students. And what this study found was that gender attitudes did become more progressive as a result of the school-based discussion, both in the sense that gender attitudes improved, and then self-reported gender progressive behavior also improved, with no effect on girls' aspirations, but very promising results. And in this study, they actually did do a heterogeneity analysis using some of our traditional common methods. And they find that, in particular, they look at the difference in the groups between boys versus girls and based off of parental attitudes. And they do find, they don't actually find a difference based off of gender, except for in the case of boys' gender equity behavior changing more so than girls'. And the way that they did this traditional analysis was using an interaction term for the treatment times the indicator that they're trying to look at the difference between. So for instance, they did treated times female as an indicator for the difference between boys versus girls' treatment effect. And so this is like a very common way of looking at and assessing heterogeneity in our impact evaluations. But the main point here is that the researchers had to decide what to look at the outset. And so they were looking at what they think is most important, or that they're most interested in finding the difference between, or which groups based off of which characteristics. And so in this case, they were most interested in looking at the gender and parental attitudes and how those affect the treatment. However, we might want to look in more detail at differences as a result of other characteristics as well. And so this is where the causal forest methodology comes in. From this study, they collected a lot of different covariates and characteristics, data on different characteristics of the individuals in the study. And so we're able to expand on these results by applying a causal forest methodology to look at those different characteristics as well. And so what this might look like is, sorry, there we go. What this might look like is that if we feed in all the other, or many of the other covariates, so in this case, we feed in 50 of the other covariates that they have data on, and we can get a causal forest estimate. In this case, we can see here an example of one tree within our causal forest that we fed all of those characteristics into. As you can see, it's interpreting the results of even just this tree within the forest is difficult. We can't even really see the splits or the combinations that result in the estimated effect for that combination of these splits. And so, and this is again just one tree and we iterate over multiple rounds to create the forest. So how would we even interpret these kinds of results from this model? So one thing that we can potentially do is visualize the results in terms of a persona of a person or a student that is more greatly impacted by the program on average than compared to those that are less impacted by the program on average. We will go into the details on how we got to this persona and the considerations for this interpretation in a minute. But just to give a preview of the results, in addition to the findings from the original paper using the causal forest, we find that students that are more greatly impacted by the program tend to have, their family owns a TV, they have younger siblings, younger, less educated parents, lower desired education and aspirations, more assets, and then generally more positive gender attitudes at baseline. So how do we get to this though? So just to take a step back and walk through the process of how we got to those results. One of the first steps here is touching back on what Devika discussed, is we have to feed in these variables into our causal forest method. And as with like a standard heterogeneity analysis, we have a hypothesis of the treatment varying case by the character like various intersectional identities, and we don't have a specific variable that we're expecting to be more or less relevant to the treatment effect. And so we feed in the outcome variable, we have the outcome variable, we have a treatment variable. The treatment is a value of 1, whether or not they got the treatment or not, and this was randomized, as we mentioned, in our impact evaluation design. And then we have all these other covariates that were collected for these individuals. In this case, we did have to focus on some covariates at the beginning already because there was just so much data collected. But again, we feed about 50 covariates into the model, and this includes all of the general demographic information, parent and sibling demographic information, assets, behavioral indices, and access to media. And so the model then, we feed these into the model and it proceeds to then group the students by a combination of these characteristics, which we could represent by that tree, but then we iterate over that multiple times. And the ultimate goal is that the forest the treatment effects to try and group the individuals so that have a treatment effect that are most different from one another in the final node of that tree. What first thing that we might check here when we're looking at the results of our treatment effect or causal forest is to look at the distribution of those conditional average treatment effects, which again, the conditional average treatment effect is the average treatment effect for each observation in the data set based on that final node because of the combinations that it falls into in the causal forest. And so we can just graph that distribution of conditional average treatment effects and see that there is at least some variation here from the average treatment effects vary from 0 to 0.45, indicating that we do have some heterogeneity in our sample as a result of this forest. But we want to look into more detail on, for instance, which variables are driving this heterogeneity that we see. And so here we can graph out the variables that we fed into the model that are most often used to split the tree. And so this is like the relatively most important variables in our model because they are split on the most often in getting us to that final treatment effect, conditional average treatment effect. And so we can see here that siblings' age was used to split the tree more often compared to other variables that we fed into the model. And so this is essentially telling us which variables are used most to maximize the heterogeneity, rather than the researchers selecting ex ante, oh, we want to see what the difference is between someone with a sibling with a higher age versus a younger sibling. We can actually have the model find the variables that are used most often to create that heterogeneity. And so, however, as I sort of implied earlier, we have to be careful in some of the interpretations of these results. And this is one example of that because for instance, siblings' age could be highly correlated with some other variables that are not included as most important because siblings' age is essentially proxying for those very highly correlated variables. And so it's possible that just because a variable is not included in the top as like a top driver or top splitter, it is because it's correlated highly with one of the ones that is included as a top driver of heterogeneity. One thing that is nice though is that if siblings' age is highly correlated with any of these other top drivers, that does imply that both of those drivers of heterogeneity are important for different reasons and not because they're proxying for one another. So the top drivers of heterogeneity, but we want to maybe look into those in a little more detail so we can dive into, first of all, sibling age and see how the individual conditional average treatment effects of our whole sample are plotted against sibling age and see that those with, for instance, here we can see that those with a higher or lower who are less impacted by the program. So if you have a lower conditional average treatment effect, your sibling's age is generally higher. And so this kind of, we try to answer the question of how does the individual treatment effect on average change as the covariates change individually, especially those covariates that we found to be most important in our splitting. So why does this matter though? So our siblings' age, the data will tell us, okay, siblings' age seems to be important, but we're going to need some sort of theory or additional qualitative information to help us understand why that might be. We can hypothesize, for instance, maybe we think that those that are exposed to the program that have older siblings are just not influenced as much because they already are more influenced and set in their ways based off of their older siblings' guidance and opinions. It's also possible, again, that siblings' age is highly correlated with other important variables, such as the age of parents, or education of parents, and that those factors are influencing a child or a student so that they don't feel so that they're not as impacted by the program because of those correlated variables. And so there's a lot of what's nice about the method is that we can find and look into variables that we might not originally have looked into. So we probably wouldn't have considered looking at the difference based off of siblings' age in our groups. But because the model has noted that this is actually important in driving heterogeneity, we might want to look into more detail onto why that is and explore that relationship in the variable in more detail. And so this method can help us, even when we look at not the most obvious covariates, we can find some important story about why someone is influenced more or less. Here's another quick example. We can look at the conditional average treatments effect as how they vary with assets, and we can see that individuals that are impacted more with higher CATEs tend to have higher household assets. And so that's one way we can delve into this data. Another way is that actually what we're more interested in potentially is the combination of the characteristics that are driving the heterogeneity. And so we can look at splitting the conditional average treatment effects into two groups. So people with above median conditional average treatment effects, a group of those with below median conditional average treatment effects. And then we can look at which combinations of covariates within those groups occur most often. And so in this image here, like each bar is representing how often a specific combination of characteristics, which is denoted below the bar, occurs. So when a dot is shaded in, that means that that characteristic occurs in combination with the other characteristics that are shaded in. And then the bar is how often that combination occurs. So you can see, the most common combination of characteristics for those more impacted by the program and those less impacted by the program is essentially the same. Like higher average assets, aspirations, efficacy, and desired level of education being below median. Some of these are likely not to be different just because they more often occur in our population in general. So that's just the most common combinations in the population overall. And so we can't say as much about that difference. But for instance, the second most common combination of characteristics for those more impacted is the same as the first, but excluding students with a higher desired level of education. So this is essentially implying that students with the same combinations as in the other group, as well as having a lower desired education, are impacted more than those that have a higher desired level of education. And so overall, this is just an example of a descriptive way of showing the top combination of characteristics for those more versus less impacted by the program. However, it's also still somewhat limited by how many characteristics we can actually see on a plot like this at once. Like we can only look at the top 5 where the list gets way too long of combinations of characteristics. And so this is an example of something we can look at, but we might be also more interested in the actual non-binary, more specific in these characteristics between those individuals more and less impacted. One way we can do that is through a heat plot. So we can look at the splitting our conditional average treatments into 4 quartiles, where 1 is those in the 25th percentile with the lowest conditional average treatment effects, and 4 is those with the highest impact of the program. The values in the chart then indicate that the average value of each characteristics in each group. So for instance, just focusing in on TV in the house, the first row, we can see that those less impacted by the program in quartile 1 are less likely to have a TV in their house than those more impacted by the program in quartile 4. So in the first quartile, there's that 76.76, that's indicating that those that are less impacted by the program, 76% of those have a TV in the house compared to 91% in the high conditional average treatment group or the more impacted group. So when we put all of this together, we can get a persona of those that are more impacted versus less impacted by the program. And we find that a student that's more greatly impacted by the program is more likely to have a TD in their house, have younger siblings, younger, less educated parents, more assets, lower desired education and aspirations, and then the positive gender attitudes at baseline. And this gives us essentially this picture of those based off of the characteristics that we found to be most important to splitting on for the heterogeneity. Again, I want to note that we do have to be cautious in interpreting this, though, because a drawback of the method is that it's just hard to interpret because some of these variables might be correlated with others that didn't get included in the final splitting choices, but are essentially proxying for those. That could also be explaining the differences in the high versus low group. So this is just a starting point. And we're still developing ways in which we can better visualize this and make this more intuitive. And we're open to ideas and discussion on how we can do this in an intuitive but also accurate way, and make sure that we come to the right conclusions. And ultimately, because this is data-driven, we're forced to think more about how different factors might be influencing heterogeneity and impact of a program. And it's an interesting and compelling data-driven way to do this. But ideally, even when we get to this result or this persona, we're left with this question of why and how are these characteristics actually influencing the difference? Like, why is someone more impacted by the program because of these, or why do they have these characteristics? So that's where we might want to bring in some qualitative analysis or qualitative data to help us answer that question. And I'll hand it over to Geetika to talk more about that.
Thanks, Fiona. Okay, so Fiona set the stage pretty well for what I'm about to talk about. So we're talking about, I'm sorry. There we go. Okay. So Fiona's talked about the results that we found from this causal forest experiment. And when looked at just in a silo, they don't really make that much sense. So we know that students who have younger siblings, who have lesser educated and younger parents are more impacted by the program, but why? So in order to sort of interpret these results, these were some of the challenges that we were encountering as well. In the absence of qualitative insights, we had to apply an intersectional or a qualitative lens to examine these results. So what we mean by intersectionality, Devika has already talked about, but just to recap, it's basically the understanding that an individual has several overlapping identities, which dictate the way in which they interact with an intervention or just the way that they view the world and go about their lives. So some of those identities might be caste, gender, their disability status, their education levels, or their economic status, just to name a few. But the way that these identities interact is basically determines the way that the impact that they would gain from a particular intervention. So in the case of the breakthrough study, had we had more qualitative insights, we could have been able to establish some contextual linkages and understand the underlying mechanisms for why certain characteristics came up on top. So, for example, we know from the study that out of the 15 training facilitators who were giving out the gender attitude study, 13 were male. Knowing this, had we had some more opportunity to examine or interview participants, we would have learned maybe from female students how they perceived a gender attitudes program that was being facilitated by a male facilitator. Similarly, had we known more information about how female role models in the students' lives were being perceived, the kind of impact or influence they had on students, that would also determine the way that they they had their gender attitudes, or the marital status of their older siblings who had such influential roles in their lives. So these are just some of the ways in which we could have done a deeper dive into the contextualizing the quantitative insights that the model gave us. Okay, so the overarching message that we took away from this particular exercise is that a mixed method approach is crucial for a holistic heterogeneity analysis. So this is because even if we find that statistically groups might be similar, there are personal attributes that differentiate them and make a world of difference in the way that they interact with the intervention. So these attributes, it's also important to note, differ from context to context. So we cannot sort of generalize for between combinations of these attributes and just replicate interventions between contexts, which is why there is a need to apply a tailor-made sort of approach to each intervention when keeping the target group and their attributes in mind. So this stands true not just for the causal forest method, but any quantitative approach that is being implemented. It requires to be enriched with the nuances of qualitative data because ultimately it'll help us understand the real and bigger picture of the impact. So let's look at decision-making in development evaluations if we're using a causal forest method. So suppose you are a decision maker from the government of La La Land. Your department has recently decided that piloting an intervention to eradicate malaria would be a good idea. A group of researchers approach you and propose to use a novel machine learning method that can help make the implementation of this malaria program more efficient and effective. Of course, to any decision maker, this sounds like an excellent proposition, but the method seems a little bit complex. So you ask the question, how will this actually work in the real world? So if we were to apply causal forests in La La Land for this pilot study, the first thing we would do is construct and run a causal forest model for the specifications of the pilot program. So that would mean all of the steps that my colleagues have talked about in the way that we constructed the causal forest for this particular experiment. Next, we would collect data for the full target population. And ideally, we would like to collect data for both qualitative and quantitative measures and use appropriate methods of data collection for both. Next, we would run the pre-trained causal forest on this baseline data. And this would give us the high treatment effect and low treatment effect groups that we were seeing even in the breakthrough example. Through these groups, we would be able to identify attributes of individuals that belonged in each group and make some sort of hypotheses as to why those individuals might be allocated as such. Next, to implement this intervention, we would first implement it to the high treatment effect group to understand the mechanisms that were driving the high impact. Once we understood those underlying mechanisms with the help of qualitative data and quantitative insights, we would be able to tailor the intervention based on individuals' characteristics before rolling it out to the entire population. So what this means is we realize that there is a group of individuals that experienced high treatment effect. We roll it out to them and see that they are actually benefiting from this program, and then make the changes or the tweaks that are needed to have the same kind of impact for the individuals in the group that are having lower treatment from the original program. So there are versions of the intervention that we roll out to each group. Causal forests can essentially help us identify these high impact subgroups very early on in the process of implementing any intervention, and thus simplify the implementation process. As I mentioned earlier, for a decision maker, the main constraints are always time and resources. So if there are ways to, in an evidence-backed manner, to simplify that and to make those decisions easier, I think this is the kind of data-driven and equitable and inclusive sort of decision-making that all decision makers should be employing. Knowing who benefits most from an intervention is the best way to understand how it can be implemented across a group of people. So surely through these examples, we've talked a lot about the benefits and the way that causal forest is an excellent approach, but we completely understand and recognize that there are limitations to any approach. So let me talk through a little bit of both of those. So in terms of the benefits, we find that causal forest gives us unbiased estimates Like my colleagues have mentioned, it's a completely data-driven method, so it avoids any issues of data mining. Secondly, it can assess complex nonlinear relationships that we've noticed. It gives us through the model, it gives us combinations that we would not have earlier imagined if it was driven only by the researchers' hypotheses. And last, it can sort through many covariates and determine the most important drivers of heterogeneity through its model. But of course, the limitations do exist. It does require a large number of observations. So you need to have a large data set in order to use causal forest. And sometimes it can be difficult to interpret. So Devika was showing us an example of a causal tree, which is much simpler to visualize and interpret, but is not as robust. And hence, we have to rely on causal forests. But that may be a disadvantage that we're working with. Having said all this, we do want to send you home with the final message that causal forests are a match for development evaluations and the work that you and I might be doing. So causal forests can work for us when we're conducting a large-scale RCT with a large number of observations. It can also work when we're interested in determining the heterogeneous impacts of an intervention or in targeting, in understanding who to target for a similar intervention. And it can also work when we want to understand the mechanisms behind a treatment effect, as we've illustrated through the examples that we spoke about. So overall, this is an interesting and novel method that has various applications, and we're extremely excited to be doing this kind of work and excited to collaborate with all of you if this is of interest. So please do reach out and look forward to the discussion after this. Thank you so much.
Awesome. Thank you, Geetika and Fiona, for that. I'm going to look at the Q&A. So we have one question about the study itself, which says, when you say, Stacy asks, when you say randomized among 314 schools, do you mean 50% of the schools received the treatment and 50% did not? Stacy, just to point out, we used this study, this paper as a case study for our work, so we did not actually run this program. But Fiona, do you want to take that?
Yeah,
Just to
so
say a bit about the randomization.
yeah, so this was for in the first stage, so the impact evaluation was originally randomized amongst the schools. I'm not sure if it was exactly a 50% split, but the idea is that yes, about half of the schools received the treatment, half didn't, and they randomly selected which schools would receive it versus not. But that was for the impact evaluation that we built on. Yeah.
Right. And then I'll just take the next question that Stacy asked, which is, what do you see as the benefit of causal forests versus including a wide variety of explanatory demographic variables in a regression? I think I mentioned this at the beginning. I think that is completely fine. Like, that's a totally valid method of doing the same analysis. But as we mentioned, I think two of the main benefits of this method versus the traditional method is that even though it requires a lot of observations, it is less data hungry than doing what you described, Stacey, which is adding a bunch of interactions to a regression. That can be time intensive and data intensive, because not only do you need to run those many regressions and have those many interactions, but it's difficult to find a significant effect for every interaction that's in the regression. And I don't know how much maybe you have worked with this in the past, but at least in my experience, it can get a little bit cumbersome to keep track of, what's working, what's not working. And then you tend to do multiple hypotheses because something's not working, you're trying a different subgroup, and then you have to do a multiple hypothesis correction, which sometimes, we don't end up doing. So this method kind of avoids these multiple hypothesis testing, p-hacking tendencies that we sometimes might have, where it kind of lets the data tell you what subgroups to split the data into. Then we have an anonymous attendee asking, checking model estimation and overfitting. Are there ways for you to check the model's estimation to identify overfitting? Yes, absolutely. We did not have time to show you all the different tests that we could do, but some of the tests that we showed just to check, one, actually, if there is any heterogeneity at all. And then there are some tests where you can check whether the model is actually detecting a difference between the treatment and control group. And the overfitting problem is partly addressed because of the fact that it's a causal forest and not a causal tree. So you're resampling from the data over and over again and then kind of aggregating. So it's like a bootstrap aggregation that prevents this overfitting, exactly this overfitting problem that you're describing. And then yeah, Geetika?
Sorry, I just wanted to respond to Stacy's question. So even with from a qualitative perspective, even with explanatory demographic variables, once the combinations emerge from the causal forest, it's still difficult to make those contextual linkages that we were speaking about. So having the model actually give us those combinations and then going into a deeper dive of why those linkages make logical sense, I think that would be an advantage of using causal forest, in my opinion.
Thank you. Yeah, I want to make sure I'm getting as many questions as possible. One more question. How do you know you have enough data, or how do you know you have the data you need to run this? Fiona?
Yes, I can jump in here. So this is actually a question that we also asked when we first started out reading up on this model, because it turns out that there's not a lot of clear guidance on exactly this question of like how and when can I use this. So we did a little bit of a scoping of other papers to see how many covariates and observations others that have employed this method have used. And it varies quite a bit. In general, the number of observations has to be very large. So usually it's between, I think, 700 to like 100,000 observations. But the number of covariates can be anything from like 5 to whatever, like 50, which is what we ended up having. And one limitation we noticed as we were running as well is that then clustering factors into this as well. So if you have 1,000 observations, but then it's clustered at a lower level, in our case, we had like 314 schools, that will then decrease the chances that you'll be able to find the heterogeneity or detect the heterogeneity. So yes, it's definitely a consideration, and hopefully there will be more clear answer to that question in the future, but just based off of seeing what others have done, that's generally the range that we've seen being used. And Devika, I don't know if there's a better more to that.
Yeah. I'm just trying to see what else. There's another question. I don't know how are we doing on time?
We have about 10 minutes, I think.
Okay, great. For continuous covariates that you input into the program, does the program make them binary, or do you have to input them already as binary variables? So I think there's a little bit of pre-processing that we do in order to make everything kind of even. So either we can convert a continuous variable into a binary, or we could convert it into a categorical variable, or like a numerically ranked variable. So there are some ways to sort of input that. You could also just keep it as a continuous variable. It doesn't have to be converted into a binary variable, but that's sort of the same issue as in general with interpretation of a continuous variable. If you want to be able to say above median, below median, or something like that, then you can convert it, but you don't have to. But there are some like pre-processing tools that are part of the package that we used in R that will allow you to convert your data into more like streamlined way to feed it into the model. Taisia asks, how generalizable are the identified groups? Can we really use the results to target groups differently in similar interventions as well? I know, Geetika, do you want to take that?
Sure. So I think the main takeaway is that the groups may not be the takeaway may not be as generalizable across groups. That's the main message here. We would need to tweak and tailor the intervention based on each group's identified attributes. So this might be similar for a group of individuals and hence might work for them, versus in the same community, there might be a different group of individuals for whom it does not work. I believe that in policy making, this can be seen as like a tedious process. But if the impact and the benefit to the end user is high, and that's the intended goal, then this little bit of tweaking and tailoring would go a long way in ensuring that long-term impact.
Yeah. I don't know if you can see all the questions that I've put on my screen. You're able to see them, right? Okay. Yeah, a
Not
lot of
on
questions.
this.
I'm just trying to see which ones to answer. Fiona, I don't know if you wanna pick one and answer it.
Good question.
This one
Let's
maybe
see.
by Mael Balak.
Yeah, so this is similar to the one we just answered about the number of observations. I actually,
Yeah.
I'm not sure about the dimensionality reduction. So let me just read it. So if the number of covariates is too high or the number of observations too low, would it make sense to explore using dimensionality reduction techniques to create components and feed these into the causal forest? I personally haven't worked with those techniques before, but I like the idea. I don't know, Devika, if you have any other thoughts on
Yeah.
this. But
I
yeah.
think conceptually that makes sense. We did do a little bit of that in terms of indices, like the original authors themselves had created some indices out of a bunch of questions. So that is one way to kind of collapse some information from similar covariates into one index. So that I think is a good idea. I think our general approach has been sort of try to make some reasonable decisions along the way and document them and, go back and revisit them if need be. But I think you have the right idea. Satish asked, what is the difference between random forest and this? This is essentially a random forest. It's just that we're applying it in the specific context of causal inference and in specific context of heterogeneity analysis. But and we're giving the algorithm a specific goal, but in theory, it's basically a random forest, but applied to this particular setting. And I think finally, why are some values negative? I mean, we just use some illustrative diagrams from different studies. So, it's possible that there were negative treatment effects of in some studies. So it's not necessarily, it's not a proportion value. We will share the PowerPoint and the recording of this as well. And yeah, Fiona and Geetika, if you find any questions, you can just type answers to. You should do that. Yohei asks, there are other estimators for heterogeneity such as causal BART. Can you show us the pros and cons of each estimator? Yeah, I think this field is very alive right now. And since the first causal tree idea came up, I think in 2017 or something, a lot of new methods and estimators have come out that address different drawbacks of the problem. So I have not worked with causal BART, but I think a lot of them have similar ideas. Regression trees, I think, are typically more BART, which is like a regression tree, as I understand it, is probably better in cases where maybe you have a lot of continuous observations and not so many like categorical or binary variables. So I think it depends on your use case and what kind of data you're working with. So yeah, that's all I can sort of answer on that.
There's a question in the chat from Frederick. They ask, how many, the quantity of data points needed to perform this study, how many characteristics do you capture of the public and beneficiaries? Are the data collection tools government data, specific surveys?
This relates also more to the actual impact evaluation, the original impact evaluation where they collected the data in that stage. So at least for the case study we used, they conducted a survey of the students, and that was what the covariates and the data points were based off of the responses to those, I think, household or individual surveys. And yeah, I think that's, but I think it could vary depending on how your randomized control trial, like where the data is coming from for the original impact evaluation.
Yeah, and I think a lot of people have this similar question of how many data points you need. And I would say that like whatever study you're doing, it depends on how large the treatment effect is, how whether how big of a difference you expect to see. Maybe there's no heterogeneity, in the treatment effect. It's pretty much uniform. So I think it's a little bit difficult to give like a number, but I imagine that if a government is doing a study and, we're asked to evaluate it, that size should be fine. And you will have to make some decisions along the way of like what one of the attendees said about, maybe create an indices if you don't have too many observations, and sort of selecting, if you have say 100 covariates and you don't have enough observations, maybe, filtering that down to like 40 or 50, or like indexing some of them. So there are these like pre-processing techniques that you might have to get into to make it work. One more question about, is there any method to assess our model is correctly fitted? I think we already answered this one, saying like the forest we think is helping us fit our model better than using a tree. And also just, we have our test data set, our training data set, our validation data set. So kind of just doing that training, testing, validation process, just like we would do with any machine learning technique, sort of the same method that we use to fit this model correctly. Any other questions? One more question here. Can the model be extended to include more advanced tree models or other methods if any other method offers significantly better performance, even if it's less interpretable? Would it be worth considering? I think that depends on your setting, depends on the policymakers that you're talking to. How much work would it be to interpret the model? Like these are trade-offs that we're also kind of thinking through and working through. In our experience working on this case study, we initially had some trouble figuring out what's the best way to interpret this data and not to over-interpret it. So as long as we're cautious about that and not putting too much, emphasis on, like, say, for example, sibling age and like things like that, and trying to just paint a picture of what that persona of the person looks like, I think, exercising caution is sort of the main thing here. Wow, we have a lot of questions. This is great.
Let's just do one more question. We have a minute left.
Yeah, let's do one more question. Lena asks, what made you decide to consider differential effects for a short duration program? Do you think there would be other considerations if focusing on a long-term program? Fiona, Geetika. Short versus long-term?
Yeah, I mean, I think it would be similar, right, for a longer term program. Actually, what was interesting about this study is they actually implemented the follow-up, or they're implementing this at a larger scale, the same intervention, just based off of the impact evaluation results. And so the fact that it was promising as a whole already led to a follow-up program. It's not exactly what you're asking here, I guess, but I would say the benefit of the short term is that you can find out more quickly the immediate effects and then implement something as a follow-up. But then in a longer term program, I mean, you'll see the sustainability of that program, and the characteristics. Yeah. Go ahead.
One more thing I wanted to add was that also we were thinking of it from a decision maker's perspective. Like typically they want to know if something's working or not before they roll it out on a large scale. And so from that point of view, I think they want to know the short-term effects of a program and how it's working. And then that's kind of how we decided that we wanted to, use this short-term results. And then, of course, I think if a program goes on for a long time, you could still continue doing this analysis and you'll just have more data points in it. And I think it would still be equally valuable for the government or whoever is running the program. Okay, I think we don't have time, right? Okay.
Okay, thank you, everyone.
Thank
Thank
you.
you so much. Reach out for more questions if you want.
Yep. Thanks.